Hello everyone, today we are going to learn about tensile testing. So to evaluate the mechanical properties of a plastic, like we have a plastic roll here, we can evaluate the mechanical strength or flexibility or toughness of the plastic using tensile testing. So just before we understand the whole process and the instrument and more technical details, let's first talk about plastic film, the role and the orientation of the molecules. So what you see right here, you have a roll. Now the film is rolled over. When the film is made, it's coming out of the die of the extruder. The polymer is coming out of the die of the extruder in this direction, and then it's winded, right? So the molecules and the polymer chains primarily they align in the machine direction. Now sometimes we have processes, sometimes we have accessories to orient the molecule in the other direction as well. So this is your primary direction of the orientation of the molecule, but then we can also orient in the other direction as well. So this primary direction of the orientation of the molecule in which polymer naturally tends to flow is called as machine direction. So if you look at the roll, the direction of the winding of the roll, so that is your machine direction. So let me draw it right here. So this direction right here is your machine direction. And the other direction that you see right here, the direction perpendicular to the machine direction, that is called as cross direction or transverse direction. So we are gonna test the properties of this plastic sheet I have. And so first thing I'm gonna mark on the plastic sheet is machine direction and cross direction. So this is machine direction and this is cross direction. And why I am marking the two directions in the plastic? Because I am expecting, because of the different orientation of the plastic molecules, the strength, the toughness, the elasticity of the polymeric material will be different in different directions. So the other word to say is isotropic or anisotropic. So isotropic means it has similar behavior or similar properties in both the directions. Anisotropic is you have different behavior, different properties in the different direction. So in the plastic, we are not expecting similar properties in both the direction. So that's the first thing to start with. The second thing that we have is to measure the thickness of the plastic film. So we have to normalize for the thickness. So think it this way: if I am stretching 2 mil or 4 mil or 6 mil film or sheet, the values, the performance of the material can change. So we normalize for the thickness, so we get a fundamental behavior or the property of the plastic. So we're going to learn about those kind of things as well. So let's start with the thickness measurement. We have a device called micrometer. So let's go to micrometer and let's learn how to measure thickness of a plastic film. I have a micrometer right here, and naturally the first thing is to switch on the machine. The red button right here, you press it and it's going to switch on the machine. You see some numbers here. The numbers here are represented in mil. So if you haven't heard it in the other classes before, mil is 1/1000 inches. 1 mil is 1/1000 inch. In other words, 1 mil is 0.001 inches. And there is no connection between mil and millimeter or mil and micron. So sometimes students confuse it. Mil is same as thou. So THOU. So 1 thou is also 1,000 of an inch. But particularly in the plastic industry, we use mils. That's the term we use. So you have the units right here in mil. The first thing that you do when you do, for example, any measurement, like for example, you have a balance, you are weighing. the first thing that you do is zero the instrument. So the same thing we are going to do, and you see the zero button right here. So to zero, first we test and close the platens that you have right here. Once the platens close and you have a number here which is stabilized, right now I'm seeing 266.82 mils. So our platens are closed, there's nothing in between the platens, so it should show zero. So I am pressing the zero right here, so we have 0.00. so now it's zeroed. Now we can open the platen and we can insert the plastic film, and I can press the test button and measure the thickness. You can see it's showing 2.78 mils. So we were expecting close to 3 mils, but there is always some variation in the measurement. So you can, it's always advisable to take multiple readings whenever you're doing any experimentation, to take multiple readings and utilize average numbers for that purpose. So we'll switch off this machine and we'll go to the next device or tool, which is to prepare sample which we can utilize for the test, and that is a cutter, which is what we call as 1-inch cutter for tensile testing. So that's on this side of the lab. So you see right here this cutter. So I can put the plastic between this holder right here and the base right here, and then I can cut the sample. Now we have different directions, machine direction and cross direction. So remember and always mark which direction you're cutting your sample in. So this is my cross direction, so I'm cutting a sample first in the cross direction. So I have this strip which is already cut, so I can easily separate it with the help of scissors. Before I do it, I want to take advantage and I want to also cut in the other side as well, so I don't have to come back right here again. So I am inserting the sample again in the other direction and I'm cutting the sample. Now with the help of scissors right here, I'll cut and mark my machine and cross direction samples. So this is my 1-inch wide sample in the machine direction. So I'm going to mark it MD. By the way, this plastic is polyethylene. And then I'm going to cut the sample in the other direction. So I got 1-inch strip in the cross direction, so I'm going to mark it as CD. So our samples are ready. So we have just cut one sample each in each direction, machine direction and cross direction. But actually, if you're doing any experimentation, less than 3 samples do not make sense, because at times you have variation in the testing, if there could be errors. So to address those kind of things, it's always advisable to have at least 3 samples tested. This is just for your demonstration. We'll just look at one sample right now. So before we get going, let's talk about some of the basic ideas in the tensile testing. Let's learn about some of the basic terms in the case of tensile testing. Stop. So what we are doing is we have 1-inch strip. So this is paper. You can test any material, but we are primarily going over plastic. So you have 1 inch strip and you are applying force, you're pulling it. And when you're pulling it, you are pulling it at a fixed speed. So as a function of stretch, your film will experience load, right? So the instrument is going to measure two things. One is how much this film is stretching as a function of force or load. So let's say our force is on x-axis, right? And our extension of the material, sorry, let me say it again. Our force is on y-axis and our extension is on x-axis. So what is the unit of extension? It's length, right? So length, let's say it's inches. And units of force, force you can have newtons, right? Or you have pounds force. So let's say I have pounds force, right? Now, as I mentioned a little while ago, when we have force. Now, is that a true measure, like of the stress in the certain areas of plastic? Maybe it's not. Why? Because a little while ago we talked about, let's say if I'm testing 1 mil thick film or 2 mil thick film or 3 mil thick film, and I am measuring the force numbers. So the force could differ with the thickness of the sample. So we have to adjust, keeping in mind the width of the sample or the thickness of the sample. If I do not use 1 inch, instead of 1 inch I have 1.5 inches or half an inch, and so the force can change. So how do we normalize for force? Instead of force, we have force per unit area, and this area is area of cross section. So what is the area of cross section? It is this, the cross section is right here. So if I have this Sharpie, this circle, that's the cross sectional area right here. So so in this case, if you have a strip like this is cut like 1 inch wide, and the plastic that we just measured, it's almost like a 3 mil thick, right? So our area would be 1 inch times 3 mil. So what I'm trying to say is, instead of force, we measure the concentration of force, which is stress, or it is the pressure, right? So stress is force per unit area. So you have stress right here, which is force per unit area. And in our case, we have area of 1 inch times 0.03 inches. And why 0.03 inches? Remember, the thickness is 3 mils, and 3 mil is 3 by 1000 inches, right? So this is our area right here. So we can, instead of force, we can represent our y-axis in the terms of stress. And what would be the units of stress? It's force per unit area, and force is in pounds, lbf, and area is in inch square, right? So pounds per inch square, and the other term for that is psi, right? So our force, instead of force, we have stress, and instead of pounds force, our unit becomes psi. So, and our x-axis, here we are talking about extension, right? But think like I am stretching a sample which is 2 inch wide, and I'm measuring how much it is stretching, versus I start stretching a sample 5 inch wide. The stretch behavior of the material can also change how long specimen I'm testing. So we have to also normalize for what are we stretching. So extension, we can represent it as the change in length. Let's say delta L. Delta L is change in length or extension. So if we normalize it with original length, delta L by L, so we start with X inches, let's say 2 inches or 5 inches. Let's say that is L, right? So we normalize, and if we multiply it with 100, that is called as percentage elongation. I think I'm ready.
Okay.
So instead of that, we got elongation, which is in percentage, right? So as we stretch the plastic, we get a curve. Now I draw a particular shape. The shape would depend upon the kind of material you are testing. What you have is initially a linear portion. Like you have this region right here, you have a linear relationship between stress and elongation. Now, sometimes you do not have word elongation. Elongation is in percentage. Sometimes you have strain, and strain is change in length by original length. Now, if I multiply strain with 100, I get percentage elongation. So when you have linear relationship between stress and strain, this region is called as elastic region, and there would be some limit of this linear relationship. So the point where this linear relationship between stress and strain ends, that is called as proportional limit. To elaborate a little more, what do I mean by linear relationship? Let's just throw some numbers right here. So I got one psi. I got 1 psi force, right? And if I got 1 psi force, because of that, let's assume I got 5% elongation, right? Now, if I have 2 psi, then I have 10% elongation. I have 3 psi, I have 15% elongation. So that's what I mean by linear relationship, or we also call it as proportional relationship. So stress is directly proportional to strain in this case. So now this is the proportional limit. This is where the linear relationship ends, and generally this proportional limit, it also coincides with what we call as elastic limit. So up to this point, your plastic material is having elasticity. So what is elastic? Elastic is a material which you stretch. Once you relieve the stress, it goes back to its original shape, right? That's what elastic does all the time. So if I cross this limit, then I am inviting permanent deformation in the plastic. Plastic is never going to return back to its original shape. It's not going to come back its original dimensions. So let's assume this is 1, 2, 3, 4, whatever this number is. Let's say this is 5 psi. This is 2, 3, or 4.5 or 5 psi. Once I overshoot 5 psi, I'm not going to go back to the original dimension. And the point right here, this is called yield point. And what is the yield point? Once you overcome that point, then the chains, they start uncoiling and they start stretching. The plastic material starts stretching below the load that's right there. So you see the load is going down right here, the stress. So the plastic can even stretch even at lower load right there. So that's what you are experiencing right here. And the point right here, this is the last point on the curve, and that is where the plastic breaks, right? So this is what we call as break point. Let's stop right here. So the first thing that we do, we switch on the computer, and we have a computer screen right here. We have a power button on this side to switch on the hardware right here. And these are the grippers to grip the plastic film. And for these grippers to work, this is by pneumatic pressure, by air pressure. So it has to be connected with the air. And you see the valve right here. So this is a ball valve, and you have to open, you have to align the way it is. So this is the open position, this is closed position. So you make sure the air supply is going into the grippers so they can work properly. The power is on, and then once the power is on, you switch on the software here, the Blue Hill 3 software. So I'm double clicking on this software, and we'll wait for the software to boot up. So the distance between the two grippers right here, this is also known as grip separation. So that is the length of the film that you are stretching. And when I was explaining on the board, L, so that is the L. So it could be set at a particular number of interest. So those numbers are dictated by standard, ASTM standard. So for testing thin plastic films, we have a ASTM standard called ASTM D882. So a copy of that is also available on our CalPoly's library website, so you can download that. So the information of the grip separation, we can add it into the software as well. So it does the numbers, it does the number calculation for us, like stress or strain, other things. So we'll input that information. Let's check if the grippers are working or not. So you see the grippers are closing, right? So they are working okay. So both the grippers are closed. I'm opening them up. So now we'll set up the program. Once we set up the program, we'll mount the plastic between the grippers and we'll test it. So you see right here, once you open the software, it's showing you some numbers like extension and load values. And you know, we can always balance the load when we are ready to test. It's not going to make a huge difference. Also, you see the method right here. So let's check the method we want to use. There are already templates right here. It says ITP 341 tensile testing for polyethylene. So let's get into the template and see what are the settings or the parameters. And you see there are various tabs right here, and we have test control. Let's see what we have here. So test, see it's saying 20 inches a minute. So that is the speed of the grip separation or the speed of the testing. So again, as I said, you have ASTM standard you utilize for providing the parameters. So generally you have a very elastic material like polyethylene. We test it at a high speed like 20 inches a minute. When you have elongation of a material, expected elongation below 100 but above 20. If I remember right, then we test it at 2 inches a minute. And for very brittle material like plastic, like PLA, where the elongation is very limited, under 20% or so, then we go by half inches a minute. So depending upon the plastic we're using, we alter the speed. Also for the brittle materials, the distance between the grippers, we change it from 2 inches to 5 inches. So that's how we test. And you can look at more details in the ASTM standard. So let me grab the sample, we'll mount and we'll start the testing. Here I'm going back to Blue Hill. I'm going to the test. I'm opening up the test method. And let me give it a name. Let me say LDPE 341 trial, right? Or whatever, 341. Let's say LDPE 341 PE. That is the name I'm giving. So the information I'm providing, this is going to save the data with this name. So the data will be saved in a digital format. I can pull the data out and I can use it. I can draw graphs, figures, do analysis, and I can do a whole lot of different things with that data. So the name is provided. I go to next, and I can feed in more information like company, whatever. It could be anything. It could be Cal Poly, it could be any companies. It's all for my reference. Or it could be a name of the plastic company. Let's say this is Dow Plastic, right? Or Dow Grade XYZ. So I can feed that information, laboratory name, ITP 341. So this is again for my reference. I can feed anything. Thickness. Now here I can enter the thickness. It's 3 mils, or for example, width is 1 inch, length is 2 inches. So I have fed the information. Let me grab this sample, mount it, and let's run a test. So I picked the cross direction sample first. It was an ideal length. I didn't have to cut it, so I picked it first. And here I am mounting the sample, and I'm closing with the help of the paddle. I'm closing the grippers, and I want to make sure the film is upright, and also I'm not stretching it too much. I'm not applying any stress. Now I'm ready to test the film. I balance the load, I zero the extension, and then I go to next, and you see the play button right here. I can say it here, cross direction, the sample specimen name, and I can press the start button. And now you can see the film is being pulled by the sample, and a corresponding graph is also being captured. The plastic is really elastic, and it already broke. You can see there is some portion underneath right here, and now it did not automatically stop. I had to manually stop it, but in general the sample breaks. It's picked up by the machine, and the top head that's moving, it returns to its home position. So I'm going to open, I'm going to take out I'm going to open the grippers, and I'm going to take out the broken sample. Now let's move it back to its position. How do we do that? We have a return option right here, and once I press the return, it's coming back to its original position. I was expecting it to automatically do it. It didn't do it. So But this can be done by changing some settings, so it can experience there is a break in the sample. So this is the graph that we got right here. I was talking about the stress strain. Right now it's load versus extension, right? So that's what it's plotting right now. I can change that with the settings. It's doing the calculation, like whatever number I'm looking for, I can set this up that I only get those numbers right here. So whatever was set in the template, it's coming up right here. So let's talk a little bit more about the specifics of this machine. I already talked about you have a power button right here. You have pneumatic grippers, and you have air supply to open and close these grippers. So this gripper is stationary, this gripper is moving, and you can see the moving head right here. Also, now I don't want the gripper head to go and bump into the lower gripper. It's going to damage the machine, and I don't want this to hit to the top of the machine. Now what we have right here is what we call as load cell. So that is going to get damaged if we hit these, if we hit the parts of the machine into each other. So we have a protection right here. When this arrow metal piece going to hit this yellow point or yellow trip button right here, it's going to stop the machine. It's not going to let it bump, but it can be moved up and down. So it could happen that somebody has set it really low, it still bumps into each other. So we have to take care of that. Also, you see on the top, you have a yellow button. That's yellow trip activation mechanism. So that's to make sure it's the top head is not hitting to the top of the machine. Also, we have an emergency button right here. If for some reason the machine is not able to stop, you can press this power button in, and you can stop the machine as an emergency. So to engage this button, you can push it in here, and the emergency error would pop up. You can also disengage by turning it around as well. So you have a 5 kilonewton load cell right here. The different load cells can be mounted on this machine as per the need. So if you have something very, very sensitive, then we have like 500 kilonewton load cell as well. Sorry, we have this is 5 kilonewton, so we have 500 newton load cell as well with us, so which is almost like a 100-pound load cell. So we can also test samples with that. So